Alright everyone, in this video we're going to be learning how to write a rate law expressions using elementary steps. So we have learned how to do the rate law expressions using initial rate methods, and another way of finding the rate law is by looking at the elementary steps whenever they are given for an overall reaction. So when you are given more than one elementary step, the rate of the reaction is going to be determined by the slowest step. Another way of saying your rate determining step, so also called an RDS, is going to be the slowest step, not the fastest step. And you're only going to be focusing on the slowest step in that particular case momentarily. And then also, make sure you never have the intermediates in the rate law expressions, and also be able to figure out what your intermediates are and do not have those intermediates in the rate law expressions. You can, however, have the reactants, you can even have the products in the rate law expression, and even you can have the catalyst in the rate law expressions, but you cannot have the intermediates in the rate law expressions. So let's look at two examples. In one example, I'm going to be looking at a reaction where I'm given two elementary steps, and in that case the first elementary step is going to be the slowest step, and turns out your life is going to be a lot easier when the rate determining step is indeed the first step, because then you don't really have to worry about what's going on in the next step. So suppose I have this overall reaction where this NO2 react with CO makes NO, well, it's going to be NO2 rather. Well, it's going to be still NO, but this CO is going to be 2 there. So I didn't write that properly there. So it makes it carbon dioxide, not carbon monoxide. So when I'm looking at these elementary step, so the first step is going to be the NO2 reacting with another NO2 molecule, and it's going to be making a NO3 plus NO. And then the second elementary step is going to be your NO2. Since it's the intermediate that's produced in the first step, it's going to get used right away in the second step. So your NO3 is going to react with carbon monoxide. So when it reacts with carbon monoxide, it makes NO2 plus CO2. And make sure your overall reaction comes out to be the same as you are given initially. So you do have a couple of things going on here. So we can clearly see that this NO3 is going to be your intermediate there. And then in addition to that, also know that you have two NO2s on the reactant side, but there is one NO2 on the product side. So I can just circle this around here, that one and that one. So that would cancel out. So when that cancels out, what's going to be left behind would be the NO2 plus CO, and that's going to be going on to make NO plus CO2. So your elementary steps must add up to the overall reaction. And in addition to that, what we are told that your first elementary step is going to be the slower step, and the second elementary step is going to be the fast step. So we only going to be focusing on the slowest step, and if your first step is indeed the slowest step, then you don't really have to worry about what's going on in the next steps and so on. So when I'm writing the rate law, I can say, since in the elementary step first one, the rate constant is just going to be maybe K1 here. So I'm going to go ahead and write down rate equals K1, and you don't necessarily have to write down K1, you could also write down K, just because you're not really focusing on the second step as it's the fast step. And then I'm going to be going ahead and writing down whatever you have on the reactants in this particular case. So you got NO2, and you got two NO2s, so what that means, I'm going to have a power of 2. Now, why do we take the coefficients here? So we're gonna have a coefficient of 1 here and a coefficient of 1 here. So those two together will make the power of 2. Now recall, if you given an overall reaction, you do not take the coefficients of the reactants as the power when you're writing the rate law expression. However, when you're given the elementary steps, and in the elementary steps, focusing on the slowest step, you will be able to use the coefficients in the elementary steps as the powers. So that's why we use this as the power here. So this comes out to be NO2 to the power of 2. So that's going to be your rate law expression. And we don't really have to worry about what's going on with the second step because that's your fast step. So overall, this is going to be a second order reaction. So I can write down second order reaction, and it's going to be second order with respect to NO2 only. The carbon monoxide is not going to be the rate, is not going to be a factor in terms of determining the rate, or another way of saying the reaction is going to be zero order with respect to carbon monoxide. Okay, let's look at another example where you have multiple steps, but then your first step is not the rate determining step, but rather your subsequent, maybe the second step or the third step is going to be the rate determining step. And I just wrote down a generic example here. So I got an A reacting with 2B making AB2, and we're given two steps where in the first step the A reacted with the B to make an AB, and this particular one is going to be a fast step. If you have a fast step before your slow step, it's always assumed that that particular fast step is going to be an equilibrium, so it's going to be an equilibrium fast step. Okay, and then in the second step, this intermediate that we just made, so remember this is going to be your intermediate here, the AB. The intermediate that you just made is going to be reacting with the B to make an AB2, and that's going to be indeed your slowest step. And make sure you add these reactants and products up to have a very same reaction as that of the overall reaction. So I can do A here, and I got two B's overall, so one B here, one B here. So it's going to be 2B, and then it's going on to make an AB2 here. Now, how do you really write the rate law expression for this particular one? So remember, we first focus on the slower step. So when we focus on the slower step, and I'm going to call this K2 here since this is in the second step, the rate is going to be equal to K2, and then the concentration of AB to the power 1 and the concentration of B to the power 1. Remember, both AB and the B has a coefficient of 1, and that's why we're using those coefficients here in writing the rate law expression. Now, what's the problem with this particular rate law expression? Well, we can clearly see that we got this AB right there, and that's actually an intermediate. So we can't really have an intermediate in the rate law expressions. So what we're going to be doing, anytime you have an intermediate, you go back to the previous step to get rid of that intermediate. So your previous step, which is the step 1, we know it's in a fast equilibrium step. So in equilibrium, so let's go back on to the step 1, which is going to be a fast equilibrium step. So we know in that particular case, the rate of the forward reaction is actually going to be equal to the rate of reverse reaction. So that's what the equilibrium steps really means. The formation of the products and the formation of the reactants takes place at the same rate. So another way of saying, if I'm losing 5 moles of A and 5 moles of B to make a total of 5 moles of AB, then another set of 5 moles of AB must be going back to make the A and the B, and so that the concentration kind of stays at an equilibrium. So when we have an equilibrium reaction, that does not necessarily mean the concentration of A and B is going to be equal to the AB. What equilibrium really means, their net concentration does not change whatever you have in that particular equilibrium. So when I'm writing the rate of forward reaction, I can say this is going to be K1 equilibrium rate constant K1 for the forward reaction, and for the reverse reaction, when it's going backward, I can write down K minus 1. So for the forward reaction, I would go ahead and write down K1 and then go back and look my reactants there. So my reactants in this particular case are going to be A and B. So A has a power of 1 because the coefficient is 1 for A, and B also going to have a power of 1 because the coefficient is 1 in front of the B. And that's going to be equal to the rate of reverse reaction. So now when we're looking at the reverse reaction, your AB is going to be the reactant for the reverse reaction. So I'm going to go ahead and write down K minus 1 there, and then AB to the power 1. So we're going to be using this particular equation to eliminate the AB that we have found in the rate law expression that we have written down for the second step so far. So what I'm going to do, I'm going to rearrange this. So when I rearrange it, divide both sides by K minus 1. So it's going to be K1 over K minus 1, A to the power 1, B to the power 1, and that's going to be equal to the AB, the concentration of AB to the power 1. And you don't necessarily have to write down power 1 if you don't want to. It automatically means that it's 1 if you don't write anything on it. So that means if I go ahead and look at if I go back and substitute this AB onto this first equation, the rate law expression that we have written down, that's going to be rate equals to K2. And then for the AB, I'm going to go ahead and plug it in K1. I can probably just copy this down for the sake of time. So I'm just going to plug this one right in here because that's being placed in place of AB. And what's left still there? Well, remember there is still a B to the power 1 that's coming from this particular one. If I show with a different color there, this B is still going to be this B1 right there. Okay, so then just kind of go ahead and simplify and see what we got left over there. So it's going to be rate equals to this, all three constants we got here, K2, K1, K minus 1, they all going to be constants. So if you multiply all these constants, you're still going to get a constant. So I'll just write down K instead of writing all those K1 and K2. And then I will have A, it's going to be first order, and then B, now it's going to be in a second order. So this is going to be your overall rate law expression for this particular reaction. So that's how you're going to be writing the rate law expression when your first step is indeed not the rate determining step. Whenever the first step is the rate determining step, the life is easier. You only focus on the first step, and whatever you see in the reactants will take part in the rate law expressions. But whenever you have like maybe a second step or even like a third step as your slower step, you always are going to have to go back to the previous steps to get rid of those intermediates like we did in this particular case. All right, so hopefully this was helpful. If you have any questions, feel free to leave any comments in the section below.